6 today. Okay, chapter 6, location and perturbation of eigenvalues. Location and perturbation of eigenvalues. Okay. Okay. Location of eigenvalues, chapter 6. Okay. In chapter 6, location of eigenvalues. Okay. For the case of diagonal matrix, easy to know what is the eigenvalues and where that eigenvalue is located, because the diagonal entries just are the eigenvalues. Okay. But in general, we have to work a little bit. One important observation is the eigenvalue of a matrix is a function, continuous function of entries of the matrix. That's the key observation. Okay. In many of the problems, including differential equation, we may not need to know exact value of eigenvalues. We may only need where those eigenvalues are located. For example, for a criteria for the stability of the linear system of equation, if the real part of all eigenvalues are negative, then the linear system of differential equation is called stable. Okay. So like this. If this is the complex field, then if all eigenvalue of that matrix, the corresponding matrix is in this side, then that system is called stable. And also, the positive definite of a Hermitian matrix is characterized by all eigenvalues are positive. That means all eigenvalues are on the right-hand side of the x-axis. Okay. So, in most of the case, we may not need the exact value of eigenvalues. We just need where the eigenvalues are located. For example, stability, positive definiteness, negative definiteness, or positive semi-definiteness, etc. Okay. The first main theorem of chapter 6 is Ch6 theorem. Okay. This theorem was first showed by Levy in 1881. In 1881 by Levy first. Then Desplanques generalized that theorem in 1887. And Ch6 reinterpreted Levy-Desplanques theorem to a problem of location of eigenvalues in 1931. That's the Ch6 theorem, which is the first theorem on the location of eigenvalues of a given matrix. Okay. Here is the survey of the problems on the location of eigenvalues. 1881, Levy gave a first theorem of this kind. In 1887, Desplanques generalized Levy's theorem. in 1900, Minkowski also had the Levy's result independently. He got the same result by himself. And in 1903, Hadamard also found the Levy-Displancus theorem by himself independently. In 1900, Bendixson found the eigenvalue bound, which is the corollary of the Hadamard theorem. Okay. In 1902, Bendixson's theorem was generalized by Hershey. All those survey was given in the book, The Survey of Matrix Theory and Its Application, by Marcus and Mintz. This Marcus and Mintz are two of the 3M, the author of 3M notations. Both of these two, including Moyes, those three professors whose names start with M, were working at the University of British Columbia in early 60s. Okay. You can find all these survey in their book, page 140. Okay. In 1931, Gelsigorin gave a reinterpretation of Levy-Displancus theorem to tell the inclusion reason of eigenvalues. That's called Gelsigorin reason. In 1937, Ostrowski generalized Gelsigorin theorem by using the overs of Cassini. It's kind of it's elliptic reason. In 1946, Brouwer generalized the Gelsigorin theorem for complex matrix. This is important here. In 1949, Olga Taussky of Caltech generalized Gelsigorin theorem in a correct way. From here to here, there has been a lot of research was done on the location of eigenvalues, generalization of this, because this idea is so simple and it is so powerful. So many mathematicians try to generalize the Gelsigorin theorem, but many of those efforts were failed. In 1949, Olga Taussky found the correct generalization of Gelsigorin theorem by introducing the concept of irreducibility, using the new concept of irreducibility concept. Okay. She got the right generalization of Gelsigorin theorem. Okay. In between, from 1931 to 1949, there was a lot of tries on the generalization of eigenvalues. Some are the generalization of the Gelsigorin theorem for the block matrices. Yeah. Okay. In 1951, Ostrowski gave another generalization of Gelsigorin theorem. And it took a long time to generalize the Olga Taussky's generalization. In 1982, Richard Brualdi gave the generalization of the Olgatowski's theorem in a very general form by using the graph theoretical approach with the new concept of weakly irreducible in 1982. Brualdi gave a proper generalization. Okay, let's start with some notations. Let A be an n by n complex matrix. Ri with a summation, there is a Ri the summation of aik for k's absolute value of it. So this is the terms in the I's law. So this is the absolute low I's law sum. Yeah. So this is the entries of I's law. There is absolute value, and these are the sums of the entries in the I's law. So we call this is the I's absolute low sum. I's absolute low sum. Similarly, J's absolute column sum is defined in this way. This AKJ, absolute value of it, we add all those from k is equal to 1 to n. Then we write it as CJ, and we call it a J's column sum. J's absolute column sum. And here, Ri prime is defined to Ri minus the absolute value of the I's diagonal component, diagonal entry. So what this means is we deleted the diagonal, the value of absolute value of diagonal entry from the I's low sum. So we call this is I's deleted absolute low sum because we deleted the value of the diagonal entry. Similarly, Ci prime is defined in this way. We deleted this value from the I's absolute low sum, so we call this is I's deleted absolute column sum. Okay? Okay, then capital R is defined as the maximum of those Ri's. Maximum of all I's absolute low sum. Okay. Maximum of absolute low sums. We define it as just R. And C is called the maximum of absolute low sum. Okay. Maximum among CJ's. Okay. So now we have Levi-Disbranc theorem is defined. Says this: if A is an n by n complex matrix, and the absolute value of diagonal entry is greater than the deleted low sum, deleted I's low sum for all I's, then we can say determinant of A is not 0. A is invertible. This is what it says. Just by checking, comparing the magnitude of the diagonal entries and all others in the same laws, then we can tell the invertibility of the given matrix. This is a very interesting theorem, and proof is so easy. See, by the way of contradiction, suppose determinant of A is not 0, is 0. Suppose it is singular, then we draw a contradiction. Suppose the determinant of A is 0, then there exists a non-trivial solution X, isn't it? And then there exists some R, that absolute value of XR is greater than or equal to the absolute value of all others. Because X is a non-zero vector, it's a non-zero vector, so some are non-zero. So there exists some non-zero xr whose absolute value is greater than all others. Okay? Then think about it. Think about ARR xr and take an absolute value of it. Then this is, since this is a zero vector, so summation of this plus all, summation of A Ri Rj xj from j is equal to 1 to n is equal to 0, isn't it? So we just move one in, we just leave one in on the left and move all others to the right. Then we have this, and we just take an absolute value. Then these are same because it's all, both sides are all positive. Okay, but as you see here, triangle inequality gives us this. Okay, but as you see, this xj is always less than or equal to the absolute value of xr. So we can replace this with this. But what is this? This is the low sum, r's low sum, and deleted, and without the value, absolute value of the diagonal. So this is a deleted r's low sum. Okay. What this says is this here the r xr's and xr's are gone because they are non-zero, so we can cancel those both sides. Okay, so this and this is gone. Then this inequality is left. This is what we have, isn't it? This is what we have. But this occurs a contradiction to the assumption that we had. So this occurs a contradiction. So this cannot be happened. So determinant of A shouldn't be 0. So this gives us a clear the criteria to be a non-singular matrix. Gelshigoryan in 1931 solved the same problem, same theorem, in the other way. Let A be an n by n matrix. And he found all eigenvalues, set of eigenvalues, is in this region. He gave this theorem. All the eigenvalues, set of eigenvalues are in here, in this set. This is a union of circles, isn't it? This is a variables, and this is a center, and this is a radius, isn't it? That's the inside of the circle. Each of these are the circles, and union of those circles. This is called the G of A, Gelshigoryan region. Each of these is a disk. I is in here, and deleted low sum is a radius, isn't it? And inside of it. So we call this is a DI of A, disk, Gelshigoryan disk. Okay. And the boundary, this border is called the Gelshigoryan circle. The union of all those disks are called a Gelshigoryan region. Proof. So simple. Let lambda t is an eigenvalue of A. Lambda t is an eigenvalue of A. Then what do we have? Determinant of lambda t I minus A should be 0. Isn't it? Now lambda t, if the eigenvalue is a solution for the characteristic equation, then by the Levi-Disblanc theorem, we should have this. Isn't it? Here. Levi-Disblanc theorem says if it's a strictly if you have a strictly inequality, then determinant is not 0. So if this is a 0, then we should have this. So we have determinant is equal to 0, so we should have this inequality. not that. And we of this matrix instead of just A. This is matrix B. What this says, lambda T is in where? Isn't it? Here. This is a circle. This is a region that AII is in here, and radius is this. Lambda T is in somewhere in here. This is what it says. Lambda T is in Gelshigoryn disk, ice Gelshigoryn disk. Okay? So, since this one is in here, so that's in the Gelshigoryn region, which is the union of all those disks. That's it. That's the Gelshigoryn theorem. It's so simple. But it is very powerful. Every eigenvalue are in the union of these disks. In one word, every eigenvalue is in the Gelshigoryn region. That's it. Gelshigoryn said every eigenvalues of a given matrix is in the Gelshigoryn region. That's it. The second part of it, so if you publish the paper in that way, then they may like the theorem, but they may not allow you to publish it because it is so simple. The proof is just so short and so simple. So even though they like it, they will not accept it to publish. So if you want to publish a mathematics paper, then you should have some difficulties in your theorem. Okay? So he added another theorem, the corollary, and another part of theorem. So this is the second part of his theorem. This says if you have something like this, if you have a 4x4 matrix and you have D1, D2, and D3 and D4, like you have these 4 Gelshigoryn disks, and these 4 eigenvalues of this matrix A are in here, in the union of this. This is what the first part of Gelshigoryn theorem says. The second part of the Gelshigoryn theorem says this. Here, this is one isolated Gelshigoryn disk. Then definitely one eigenvalue is in here, but not more. Here, this is a union of 3 Gelshigoryn disks. Then in here, there are 3 eigenvalues, and there is only one eigenvalues in here. This is what this theorem says. Suppose you have a union of k Gelshigoryn disks, then there is k eigenvalues in here, and if you have n minus k, the union of n minus k Gelshigoryn disks, then n minus k eigenvalues are in the other part. This is what he also showed. These two parts of theorem made a great contribution on the research of location of eigenvalues, which is particularly interested in the stability theory and also in the most part of the engineering. Okay. Proof is in page 345. Okay. This is a corollary. So here, the first Gelshigoryn theorem was given for the low sum. But all the proof, all the determinant and things are working similarly for the columns. So how if we replace the rows of A to the columns of A? What if? It doesn't make any change. Because determinant, they have same determinant, and all the argument works for the columns if it works for the rows. So we can easily tell the spectrum of A, the set of eigenvalues, is in the union of not only rows, but the columns as well. So if you think of the columns, then this is just same as a transpose, the Gelshigoryan region of a transpose. Instead of taking the deleted row sum, if you take a deleted column sum, same thing work. So the Gelshigoryan, the spectrum is a subset of all the eigenvalues is in the intersection of this, isn't it? Okay. These are all the corollaries. Okay, so not only here, it's also is in here. So it's we are in the intersection. Okay, here is another corollary. Then what is it? This is a spectral radius, the absolute value of the largest eigenvalue of A. That's in the maximum of this and maximum of this, which is the minimum of this RNC notation that we defined. Because the spectral radius of A is smaller than, actually, for any norms. So for the infinity norms, it's smaller than that. And A transpose, the infinity norm, matrix infinity norm for the A transpose, this is smaller than or equal to this and this. Because of that, this is smaller than this, and this is smaller than that. Okay, so it's an and. So it should be an intersection. So it's a minimum there. So this spectral radius is smaller than this. What this says is this. Suppose we have the region like that. We start from here. Okay, we start from here. Then we have a Gelshigoryan circle like this. Then here AI here, and this is RI here. Then the spectral radius does not bigger than this. This is what it says. Okay. Okay. This is this because this distance is this ONC as well. Okay. This is what that says. Okay. Anyway, we have a clear characterization for the upper bound of the spectral radius, and also the spectrum of A is similar. It's the same as the spectrum of the all similar matrices, because these two similar matrices, if A and B are similar, then spectrum of A is same as spectrum of B. Okay, they are same. They have same eigenvalues. So spectrum of A is same as spectrum of S inverse A S for any S. For any S, isn't it? So, Richard Varga at Kent State University generalized the Gelshigoryan theorem by using this fact in 1965. Okay, Mr. John, why don't you try to write something? I don't think you can get everything in your head by a word. Okay, Richard Varga got a generalization of Gelshigoryan theorem by using this simple fact. This is what he had. Let A is an n by n matrix, and D is a diagonal matrix like this, and all PI's are positive. Then it is a invertible matrix. If we multiply D inverse A and D in this way, this eigenvalue of this one is same as eigenvalue of this one, isn't it? So you try to use the same upper bound, at the the radius not only for A, but also for D inverse AD. Then deleted row sum can be written in this way. We can give a variation of it. P inverse A. D inverse AD like this. Okay. We can just give any non-zero numbers in here to have the deleted row sum. We can choose any PIs, non-negative PIs, and positive PIs, because which is same as Gelshigoryan region for D inverse AD. And also, we can do the same thing for the transpose of this, isn't it? Transpose of this. So we can change it. We can change the low PI and PJs. Okay, this is a Gelsiger region for the D inverse AD transpose. So we can give we have a lots of freedom to choose the radius for the Gelsiger disk. Okay, for example, here, let A is this matrix. Then we know the 1 is an eigenvalue and 2 is an eigenvalue. And for the second disk 2, D2, we have 2 here, and the radius is 0, so it's just 1 point. For this point, A11 here, 1 here, and radius is 1, so take 1 here, and we make the circle. So this is a G region of A, and we see these 2 eigenvalues is in this region. Okay, but let's take R is equal to P2 over P1. So let's choose P1 and P2, non-negative, positive numbers. Then this is negative, the positive. Let's see. We can choose this by choose this. We can squeeze the radius. Then by choosing it, we can easily have 2 isolated circles. We can just squeeze the radius as much as we can. So we have just circle like this. That's 1 point. So we know this is the eigenvalue. And this is a radius R for, if you choose this is a radius R for the first disk, D1. This R can be chosen as small as we want. So we can squeeze this radius as much as we can. Then how? What it happen? It is end up with 1 point, isn't it? So it will tell us 1 and 2 is an eigenvalue just by looking at the circle, looking at 2 Gelsiger disk, which is just a point with just epsilon radius. So we can roughly say the eigenvalues are near 1 and 2. We can tell without any hesitation. We can squeeze the radius as much as we can, so the eigenvalue converges to 2 and 1. That's it. Like that. So Varga's theorem is also very powerful tool to be used. Okay? And also, those PIs were arbitrarily chosen. So we can modify the previous theorem to get the next corollary. Okay. We can choose PI and PJs in any way, so we can take a maximum and minimum. We can take a maximum and minimum of, we can take min, max, and max, min choices as we can do this, because that the previous theorem works for all PIs. Positive. So what this says is, you can think the intersection of Gelsiger region for D inverse AD for all these, where these are diagonal matrix with positive entries. Okay. For all these of this property, we call this region. This is the minimal Gelsiger set. Minimal. We take all the possible choices of D to find the minimal region. We can squeeze intersection of it. Okay. This is a powerful result. We can just try everything then to draw the love conclusion for the location of the eigenvalue, even though it is a very large size matrix. And there are some exercises. Yeah. What about the skew Hermitian matrix? What about the skew Hermitian matrix? What's the eigenvalues of this? Where those eigenvalues are located? These are all pure imaginary. isn't it? Hermitian matrices are all reals. Skew Hermitian, all eigenvalues are pure imaginary. What about if it's a unitary matrix? Eigenvalues are all on the unit circle. Unit circle. What about real orthogonal? So suppose you have a real orthogonal matrix. A transpose A is equal to identity. It's not only on the unit circle. It's a real orthogonal. It's a Hermitian. So it's eigenvalues are all real. Yeah. It's on the real. It's on the circle. So the eigenvalue can be only 1 or -1. That's it. Gelshigorn region can be just these 2 points. Something like that. So we can tell. Skew Hermitian, that means all the eigenvalues are, it's not on the real, it's a whole, not on the real, it's a whole pure imaginary. So it's on the, something like this. Pure imaginary, so it's on the here. Yeah, on the here. Okay, so we can tell what is the possible Gelshigorn regions for those special matrices. This is the definition. A is diagonally dominant. That means all the diagonal entries dominate the deleted low sum. Okay? And A is strictly diagonally dominant. Is just with a strict inequality. Just the absolute value of a diagonal entry strictly dominate the deleted low sum. Then we call this matrix strictly diagonally dominant for all i's. Okay, so we have diagonally dominant and strictly diagonally dominant definitions. Okay, so one example says if the matrix A is strictly diagonally dominant, then if AII is positive, is for all I, then A is positive stable. Okay, all eigenvalues are positive. All eigenvalues are in this side. AII is in somewhere here, in here, and strictly diagonally dominant says if the deleted low sum does not exceed this distance. So it's in here. So Gelshigorn regions are here and here and here like this. Okay? So all the eigenvalues should be in this side, all real and positive, all positive of the x-axis. So A is positive stable. It's called. All those definitions, stable, stability, and positive stable, and positive semi-definite, all this comes from ordinary differentiations that you have already learned. And also, if A is a Hermitian matrix and all AI's are positive, and A is strictly diagonally dominant, then lambda is are all real positive. Okay? It's a Hermitian, so all the eigenvalues are here. And AI's are positive, and strictly diagonally dominant means the deleted low sum does not exceed the distance from here to here. So it's in here, in the middle. So all eigenvalues are here on the rear. So what this says. So all the eigenvalues are not here. Eigenvalues are here on the rear, positive side. Rear positives. Something like that. If we combine all the previous observation and proofs and theorems and corollary, this is what you have. If it is strictly diagonally dominant, actually this is what the Gelshigorn theorem, the condition for the Gelshigorn theorem. We just write it in one sentence. If A is strictly diagonally dominant, then A is invertible. And also, if A is if every diagonal entries are positive, then every eigenvalues of A has a positive real part. And if A is Hermitian and diagonal entries are all positive, then every eigenvalues of A are real and positive. Okay? This is what we have done so far. And theorem 6.1.11 that A has all diagonal entries non-zero. Yeah. So all the diagonal entries of A's are all non-zeros, and A is diagonally dominant with this condition. This is true for all but one value. All but one value. Then A is invertible. This is not strictly diagonal dominant. It's diagonally dominant. Diagonally dominant. But this is all, we have all strictly diagonally dominant except one row. But still, we have invertibility. This is theorem 6.1. Proofs are exactly the same. We can easily show it. Hana, why don't you try this one? The proof is in here in the book. Okay, it's same. It's almost same as what the Ch6 theorem was proved. Okay. And there are some problems, exercise in page 3.340A. So Jin and Chung and Horror do some problems. Choose two problems each to solve. Okay? In chapter 6, including page 348. Okay. Keep going. Section 6.2, Ch6 disks. We give a closer look on it. Okay, recall. Strictly diagonally dominant guarantee the invertibility. But diagonally dominant does not guarantee the invertibility. Except the one example that you show, theorem 6.1.11. If it's all strictly diagonal, except one diagonally dominant laws, then still is invertible. But generally, diagonally dominant does not guarantee the invertibility of the matrix. Okay. Think about the other DI case. If one row is strictly diagonally dominant, and all other rows are just diagonally dominant, then what happens? Think about it. This first row is strictly diagonally dominant. Okay? But here, these two rows are just diagonally dominant. But as you see, what's the determinant of it? This is 0. As you see here, just the diagonally dominant doesn't guarantee anything. Okay? But if we add one more condition, if we add one condition, then we can have invertibility. Okay. There was a lot of research were made to find the right correct generalization of the Ch6 theorem. Okay. And Olga Tausky finalized and conclude those journey of others. Okay. Here are some exercises. Yeah. So suppose A is not in any Ch6 disk of A, if and only if this inequality holds for all i's, not only one or two. It's just hold for all i's. What this says is this. If eigenvalue lambda is on the boundary, how do we boundary on the boundary of G of A. How do you call? Suppose eigenvalue lambda is on the boundary of G of A. Suppose we have this. Then the boundary is what? Here, isn't it? These boundaries in the region. Then, if lambda is on the boundary of Gelshigoryan region, then it satisfies these inequalities. I will show what it means. This is a lemma that explains what it was told. Okay. Here, suppose let A is an eigenvalue, A is a matrix, and lambda satisfies that inequality. Okay, for line. Okay, then lambda is an eigenvalue that satisfies this inequality in the previous page. Then think about it. Ax is equal to lambda x, and x is a non-zero vector, it's eigenvector. And suppose P is an index such that absolute value of xp is the maximum of among the rows, the absolute value of other row entries. Okay, then let xp is not equal to 0, and it is the maximum of all. Okay, if xp has, then if xp, absolute value to xp, xk is equal to same as absolute value of xp, then it satisfies lambda, absolute value of lambda minus akk is equal to rk prime. What this means is lambda pass through the case Gelshigoryan circle, passes through the circle, not inside. It just passes through the boundary. This is what it says. If these are same, then it just passes through the boundary of that circle. Okay? If these two absolute values are same for some k, and akj is not equal to j is 0 for some j which is not k, then the absolute value of xj is same as absolute value of xp. That's what this says is this. This gives us when one eigenvalue pass to satisfy one condition, that eigenvalue is not only one Gelshigoryan disk, it also passes through all Gelshigoryan disks that has the property. Okay, let's see. I will show it. Yeah. Suppose by the Gelshigoryan theorem, the proof of it, then lambda minus aiixi can be written in this way. Then we can take absolute values. Okay. Then by the inequalities, then we have this. This is the xp, and this is a deleted low sum. Okay. What that means, if xp is equal to the absolute value of xk, then this can be written in this way. Okay. But as you see, this was a given condition. This was a given condition. Okay. So they should be same. So they should be same. So we have this is same as this. This is same as this. Okay. And this is a deleted low sum. K is deleted low sum. Okay. But as you know, since it's x came from an eigenvector, which is a non-zero vector, the absolute value of xk is the maximum value of it, so it's positive, so we can cancel those non-zero terms on both sides. Then what do we have is this equality. This means lambda passes through R's Gelshgorin disk passes through dk. Lambda is on here. This is what that says. And second part is same, is similar. Suppose we have this, then this should be 0, and these are all non-negative, and these are non-negative. So this got to be 0. This should be same. If some of them are not 0, summation of all these are 0. These are all non-negative. Okay, suppose there are one thing is not 0. For that, then this got to be 0, isn't it? Okay. Okay. This is very simple, but this gives us some important consequences. Theorem 6.2.5. Let A is an n by n matrix, and lambda is an eigenvalue of A on the boundary of G of A. If lambda is an eigenvalue of A on the boundary of Gelshgorin region. And suppose every entries of A is a non-zero, okay, all Aij is not 0 for all Ij. So these are the two conditions. Lambda is an is on the boundary of eigenvalues, and all the entries are non-zero. Then what? Every Gelshgorin circle pass through lambda. Every Gelshgorin circle passes through. Isn't it? There's a lots of Gelshgorin circles. If lambda satisfies these two conditions, then every Gelshgorin circle passes through that point. This is what the previous observation gave us. Okay? And if Ax equal lambda x and x is not equal to 0, then we have then xj is same as xp as well. This is what we have. Okay, same thing as what we see. I will show it. I prove. Here. Okay. Yeah. So, yeah. This is so simple. Yeah. Let xp is same as the maximum. Let's say xk absolute value is the maximum value of it. So but then the second part of my lemma, the previous lemma, we know this xi and xk's are same. Got it? But the second part of the previous lemma. Then first part of previous lemma give us this. This is for all i's. That means this lambda passes through lambda minus ai is equal to ri prime of a for all I. What this says is this lambda passes through all Gelshgorin circles. Gelshgorin disks. This is what this says. That simple observation gives us a very important fact. Isn't it interesting? The one eigenvalue, if it is on with one condition, if it's on one boundary, then every other Gelshgorin circle should pass that whatever the size of the matrix is. Here, next corollary. Suppose AI is like A is a matrix, and all Aij's are non-negative, non-zero, and A is diagonally dominant, and some AI's absolute value of some AI is strictly bigger than Ri deleted low sum for n least one i's. Okay, so strictly diagonally dominant for n least one i's. Okay. Okay. Then we call it is invertible. This is a very interesting thing. Before, diagonally dominant and one strictly diagonally dominant doesn't give us the invertibility. didn't give it. Hana, before, everything is strictly diagonally dominant and one diagonally dominant, then it was invertible. But it didn't work for the other way. If one is one is diagonally dominant, one is strictly diagonally dominant, and all others are just diagonally dominant, then it did not guarantee the invertibility. But here, just A is diagonally dominant, and one row is strictly diagonally dominant with this condition. Non-negative. All entries are non-negative, non-zero. Then we could have invertibility. Here's a proof. By the way of contradiction, suppose, like, it's invertible. Suppose it's not non-invertible, not invertible. Then determinant of A is equal to 0. So 0 is in the eigenvalue, the set of eigenvalue spectrum. Okay? So 0 is not in the interior. 0 is not in the interior of G of A because D is a diagonally dominant. Suppose this 0 is an eigenvalue. It's on the border, not in the inside. Diagonally dominant like this. Okay? So it's AII here. It's a diagonally dominant, so it can happen here, but diagonally dominant. So it cannot be on the interior. So what this says is that 0 eigenvalue, since the determinant of A is equal to 0, and it's diagonally dominant, so 0 is on the boundary of it. Then, by the previous theorem, every Cauchy-Corin circle pass 0. Every Cauchy-Corin circle pass 0. But the condition, this condition, says I circle cannot pass 0. I Cauchy-Corin circle cannot pass 0. It occurs a contradiction. So this can not be happened. So it should be invertible. So previous lemma can be well used to give us the right generalization of the Cauchy-Corin circle with a condition. So all entries are non-zero. And this, think about this theorem. This is Olga Tauski's generalization of 1949. Suppose A is an irreducible matrix and is diagonally dominant, okay, with strictly diagonally dominant for at least one I. Same thing, diagonally dominant with at least one strictly diagonally dominant rows, then determinant of 0. So it's been changed. Before, every entries were required to be non-negative, non-zero. But now, Olga Tauski just gave a new definition of irreducibility. Okay. Irreducible, I think I have definition of irreducible. Irreducible. The definition of irreducible means there exists a permutation, reducible matrix. A is called reducible if there exists a permutation matrix P such that P transpose AP can be written in this way. So A1, A2, A3 here, but some zero block like this. If we can move some zero entries to the corner to make a block matrix, then we call this matrix reducible, like this. If not, we call it is irreducible. Olga Tauski found this condition and he defined. See. So proof. By the way of contradiction, suppose the determinant of A is equal to 0 with the given conditions. Then there exists a non-zero eigenvector. Then there exists an inequality for at least one value of k, like this. Then there exists some I such that ARI is not equal to 0 with this condition. It is just the easy consequences of comparing the components. Okay, then this implies R's law contains n minus s zeros, where this s is the number of j's that has the same length, same magnitude. What this means is we have n minus s zeros on the corresponding laws for s. Like this, what this says is we have zeros, the zero blocks in here corresponding to the s's. If this exists, that means A is reducible, but it occurs a contradiction for the given condition of irreducibility. So this is Olgatowski. It's proof for the generalization of Cauchy-Green theorem. Okay, the research was not done on there. They continued the work on the location of eigenvalues. So they defined the new definition of property SC. It's sometimes called strongly connected, but in the graph, but in the matrix, it is called property SC. If we say A has property SC, if there is, for arbitrary PQ in 1 and n, between 1 and n, and there is a sequence of distinct integers, start from K, P, and end up at Q. Okay. Such that all of the matrix entries, A, K1, K2, A, K2, K3, and K, m minus 1, Km are non-zero. If we find the sequence of non-zero entries, then we call it strongly property SC. This matrix don't have property SC. If you start from 2 on, you can find any sequence which is not all 0. Okay. Here, for example, if you start from 2 on, for 2 on, you can find if you start from 2, so if you start from 2, 2, then what you can choose is you start 2, 2, then you start from 2, 3, then you start from 3, 1. 3, 1 is 0, so you cannot take this one. So it should be distinct. 2, 3, 1, like this. And if you start from 2, whatever, anyway, this, from here, from 2 on, you cannot find, you can feed out the distinct numbers to have a sequence. The corresponding entries are all non-zeros. Anyway, this property SC gives us a better theorem like this, that A be a matrix and lambda is an eigenvalue, and this lambda is a boundary point of GA. Then if A has a property SC, the matrix A has a property SC, then every Cauchy-Green circle passes through that eigenvalue. And if AX is equal to lambda X and X is an corresponding eigenvector, then all the value of all the absolute value of eigenvalues are same. This is the theorem which is written in the terminology of property SC. Okay. The proof can be shown in this way. Let AX is equal to lambda X, and this XP has the largest absolute value. Then, by lemma 6.2.3, we know it satisfies this equality, and let Q is an integer between 1 and n, which is not same as P. Then if we have two distinct P and Q, then because of strong the property SC, there is a sequence of distinct indices start from P to Q, and that Q, such that all of the entries AK 1K2 to AKM minus 1KMs are non-zero. So, since this AK1, AK2, and this is APK2 is not equal to 0, so these two are gotta be same. If the two are same, then this AK2 and K3 is not equal to 0, and this K3 and K2s and Kp's are all same. But if we continue, this shows all Ki's has the same value as XP for the absolute value, then we have this equality to give us the Cauchy-Green circle. What this means is, here's a Q. The lambda is on the Q's Cauchy-Green circle. So this Q's Cauchy-Green circle passes through lambda, and these values are same. But as you see, this Q was arbitrarily chosen. That's the index which was chosen arbitrarily. So what this means is every Cauchy-Green circle passes through lambda, and all the absolute value of xi's are same. That gives us the theorem. Okay? So, or every Cauchy-Green circle passes through lambda. That can be obtained in that way. And here, this is another corollary. If A has a property SC, and A is diagonally dominant, and it is strictly diagonally dominant for at least one row, then determinant is not 0. Okay. Here, the property SC. The observation shows this property SC is not depend on the size of entries. It just depends whether the entries are 0 or no. So this property SC depends on the location of off-diagonal non-zero entries. Off-diagonal non-zero. Key is the location of off-diagonal non-zero entries. Here, the entries of main diagonal and the size of the off-diagonal entries, the exact value of the entries does not affect anything. It's not important. So we can think a new matrix, MA, which is called indicator matrix, defined if mu ij is if aij is not 0, then we just write it 1. If aij is equal to 0, then we make it 0. So from matrix A, yeah, set absolute value of A is just every entries of A's are taking an absolute value, and MA B is a matrix, and by a matrix whose entries are mu ij, and mu ij, the entries of mu ij is equal 1 or 0, whether the aij is equal to non-zero or 0. We call it an indicator matrix. Then, A has a property SC if and only if this absolute value of A has a property SC, and also if and only if this M of A has property SC. The same. If this M of A has a property SC, if and only if A has a property SC. Okay? So if we have a matrix A, then we just can think about new matrix M of A, the indicator matrix, to work to figure out the invertibility of the given matrix A. So there are some graphical interpretation and explanation of those. And think about a new definition. Suppose A is a directed graph. The directed graph of A, written as gamma of A, then the direct graph on n nodes, P1 to Pn, such that there exists a directed arc in gamma of A from Pi to Pj, the node Pi to Pj, then if and only if this Aij is not 0, and also mu ij is not equal to 0. This is actually the interpretation of those. For example, if A is a 2x2 matrix like this, then gamma of A has a 2 node, P1 and P2, and we start from 1 to 1, 1, 1, so 1, 2, so 1 from 1 to 2, and here 2, 1 here, and 2, 2 here like this, with the directed graph. And if you have this, then something like this. And you should know about it. Okay, now suppose you have this matrix, then the direct graph of that is this. Okay. For example, 2, 2 is here, from 2 from 2 here, and 2, 3 exists, so from P2 to P3, there's a path like this. Okay, here's the definition. Graph gamma, direct graph, directed path, gamma, is a sequence of arcs in gamma. Suppose, okay, in this, okay, the directed path is a sequence of arcs like this. Then the ordered list of nodes in this directed path is just PI1, PI2, PI3, PI1 start from to PI2, PI2 to PI3, PI3 to PI4. So the ordered list of nodes can be written in this way. Then what's the length of this gamma? This is a number of successive arcs in V. Okay, number of arcs. Finite. It can be finite or infinite. Gamma is called cycle if directed path start at one node and ended at the same node. Then we call it a cycle. In here we just count the simple directed cycle. Okay. And gamma is called roof or trivial cycle if the length is equal to 1. If we start from itself and come back like that, this is called the roof or trivial cycles. And those are the definitions. The next definition. The direct graph is called strongly connected if every distinct node or every pair of distinct nodes, Pi, Pj, a pair of nodes, if there exists a path, start from Pi and ended at Pj, then there is a path such that start from one node to this node for arbitrary I and j. Suppose there is a path from Pi to Pj, then we call it strongly connected. It's as itself, strongly connected. It's connected but strongly. So whenever I start, wherever I start and wherever I go, then there is a path to go. Then we call it strongly connected. Theorem says this. S has a property SC if and only if the direct graph of the matrix is strongly connected. This if and only if. So the study of matrix is just work at the study of graphs like this. Okay? Matrix A has a strong property SC, and the graph, corresponding direct graph has the similar properties. Not only A, the indicator matrix, more simpler ones. Okay. Strongly connected. There are some things to read. Okay. Here, observation. The checking checking of strongly property SC of A is same as checking the strongly connectedness of the direct graph gamma of A. Okay, so they are equivalent, so we can choose what we like to do. And in order to check it, we need some techniques. Here is just some techniques. For a matrix A, if Pi, Pj's are two nodes in the direct graph gamma of A, then there exists a directed path of length m, directed path of length m in gamma of A from Pi to Bj, if and only if the ij's component of the m's power of the absolute value of A is not 0. This is same as the m's power of indicator matrix has ij's component which is not 0. This is same. Here, this is not easy to check, find the existence of path. But this is very easy. This is 0, 1 matrix. We can just take a power without any difficulty, and we can also, it's very easy to check the some ij component is 0 or not. So with this gives us great freedom in the computations. The proof is clear. When m is equal to clearly done by mass induction. When m is equal to 1 is trivial. When m is equal to 2, we can easily check whether if this is not 0, then if n for at least one value of k, some of them are not both 0. Not both 0, are both non-zeros. If it's not 0, you understand that? Yeah. If this one's 0 and this is non-zero, and if this one's non-zero and this one's 0, then it should be 0. So we should have something that both of them are not 0 to make it. So both of them are not 0, so that means there's a path of length 2 in gamma of t. Like that. Yeah. So let's assume true for m is equal to q and show true for m is equal to q plus 1. And by the similar things, since for at least these are all both non-zeros, and if that's not 0, then the next one should also be both of not zeros. So all terms of q plus 1s should have the terms that both are not zeros. So the proofs are quite simple. With that, we can do lots of things. Suppose we call, if all entries are real and non-negative, then we call it a non-negative matrix. If all entries are real and positive, then we call that matrix is positive. Okay? Then, here's the corollary. Suppose m's power of this absolute value of matrix is positive. That means all of the entries, all aij m's are positive. If and only for each node from pi to pj gamma of a, there exists a direct path of length exactly m. Here m comes from this power m. So this corollary is not work only for the matrix itself or the cube or some. It just works for all m's. So if we need to find a path with the case length k, all we have to do is just take power of k. And from node I to j, then all we have to check whether these ones are 0 or not. That's all we have to check. So easy. So this gives this property. A has a property SC if and only if this matrix n minus 1's power has all positive entries. If and only if the I plus indicator matrix, the n minus first power, has all positive entries. Proof is very clear. Just think about this matrix. Then binomial expansion, we have this. So if and only if these are positive, if and only if, for each pair ij of nodes that are distinct, that at least one of the terms has positive ij entries. Then by the previous theorem 6.2.16, if this happens, that means there is some direct path in gamma of A from pi to pj. That means its direct graph is strongly connected. A has properties. So it all works. So actually this is what you're going to use in the real world problems. Okay, there are some corollaries, hypotheses, and there are some other observations. Okay, here is the definition of irreducibility, 6.2.21. If n is equal to 1 and a is equal to 0, then, or if n is greater than or equal to 2, then there is a permutation matrix P, and the integer, positive integer R, such that P transpose A P is like this. This is a zero block matrix of zero block matrix of size n minus R by R. Some for some R's. In the previous proof, yeah, we had S and minus S. This is irreducible. If there is a permutation matrix P, then makes this all zeros. Then we call it irreducible. If it's not irreducible, we call it irreducible. If A is irreducible, what we can do is just think about this matrix like this. Then we can think about the linear system of equation in this way. Then this linear system of equation translated in this way. We can make two different problems like this without those zeros. So we can simplify a system of linear equation with the irreducible matrix to reducible matrix to several linear system of equation of with the irreducible matrices. So if we just finish here, if we can deal with the theorem with the irreducible matrices, then we can expand to all matrices. Okay, so this is a very important condition to think. Suppose we have a reducible matrix. We make it as a direct sum. We make it as a reducible part, irreducible part, and reducible part. And think about this irreducible part is first. Then that will take care of the whole things. So irreducible matrix is what we only to think first. A matrix A is called reducible if that matrix is not reducible. Theorem says if A is irreducible, if and only if this is true. I plus this to the n minus 1 is positive. Isn't that nice? If we have a reducible, if A is a reducible matrix, this power of the power n minus first power of I plus A always have some zero in here, whatever we take the powers up to n minus 1. Okay? So this is very easy to check. Isn't it? Very easy to check. Nowadays you have computers. Okay. By just checking these criteria, you can always tell it's irreducible or not. If it's not irreducible, then you can split it to the irreducible parts. Then you can start from there. Then you can use the Olga-Tauskis generalization of the theorem. And also, that irreducible matrix work for all other theories as well. Okay, yeah, here's the simple proof. Yeah, you can do it by yourself. All the proofs are written in the textbook. And there are some other the comment to start to this. Okay, these are the proof of the previous theorem. And if we all together, combining all together, this is what you have to know. This is what you have to know. The following statements are all equivalent. First, A is irreducible. This power of the matrix has all positive entries. Same for the indicator matrix. The corresponding directed graph gamma of A is strongly connected. The matrix A has property SC. They are all equivalent. You will see this strongly connected condition in the graph theory. You will see this irreducibility condition in the matrix theory and all other applications. In that case, this is the theorem that you can use. You can easily check whether the given matrix is irreducible or not, or has property SC or not, by just checking it. Okay? And next theorem. Yeah. There's one more definition for the irreducibly diagonally dominant. If A is irreducible and diagonally dominant, and it is strictly diagonally dominant for at least one row, then we call it irreducibly diagonally dominant. Okay? Then we can have this. This is corollary by Olga-Tauski. If A is irreducibly diagonally dominant, then A is invertible. If all AIs are positive, then real part of our eigenvalues are positive. And if A is Hermitian and all diagonal entries are positive, then every eigenvalues are strictly positive. This is can be all obtained. Okay? Irreducibly diagonally dominant. First condition, irreducible. Second, diagonally dominant. And at least one row has a strictly diagonally dominant. Then we have it covers most of the previous works altogether. Okay? Okay, here are some more corollary. Yeah, this is it's easy. Yeah, this is easy consequences. Okay. Yeah, Gelchgorin theorem. Yeah, I've uploaded some of these on the web. So you can easily find it if you go back to the Gelchgorin theorem by Google search. Then you will find something already on the web. And these are the tools. These are the Gelchgorin circle tools that I made by MATLAB. Now I'm using what? Java tools. Okay. Yeah, we can randomly generate the 6 by 6 matrix, 5 by 5 matrix from -6 to 6, and this is random matrix. Then you can find the eigenvalue, and we can draw the picture where those eigenvalues are. Second Gelchgorin theorem, the second part of the Gelchgorin theorem, and these are the part of it. And also, I developed it, and I will show you later as it goes. First, the third section of chapter 6 is about the perturbation theorems. Perturbations. If you make a small change on the entries, then how the eigenvalue changes, how much it can be changed. If you move small, and then the result doesn't make big changes, then you can think it's a stable system. But if you make small, but you don't know how much it can be changed, then you can tell that system is not very stable. Okay. So if D is a diagonal matrix and E is a perturbed matrix, it's a matrix with just it's very small, something like that. If the matrix norms are very small on this, then you just add the matrix E. Then think about this matrix instead of D. You can think about the disk of this. Then this matrix may not have the conditions that you like to have. But if we add just minor changes on it, then you can generate a matrix of the condition that you can add all the condition on that matrix with just adding. It makes some changes. Then you can use the previous theorems because you can make a matrix that hold the conditions of the theorem. Then you can use the conclusion of their theorems. Okay. So, for example, observation here. So A is, suppose A is a diagonalizable matrix. It's a diagonal matrix. Then E is a n-by-n matrix. Then lambda hat is the eigenvalue of A plus E. Then there exists the some eigenvalue lambda I of A that satisfies this. Yes, yeah, can make easily since this S, this because of that. Yeah. And this is a condition number. This is condition number. This condition number is defined in this way. And A is a non-singular, then you can define it this way. If A is singular, then we define it as infinity. Then we just define K sigma infinity of it as the condition number with this matrix norms. Okay. Then we can, this is just, this comes from the properties of matrix norms, and this is the definition of condition numbers. So we can have this. What this says is, if we perturb little, it doesn't make big changes on the eigenvalues. There's not much change on the eigenvalue of the original one and others because this distance difference is very small. Okay, but and here is the definition of the condition numbers, and it has the property that it has, as you have learned already. But here, how we use this perturbation technique. When you solve AX is equal to B, even though this A inverse does not exist, if we just add a little, then this may have an inverse, isn't it? If you have some eigenvalues are 0, then if you add just a little perturbed matrix with a very small matrix norm, then you can just make a little split, the shift. Okay? Then you can think, instead of thinking this one, you think this one. And you deal with whatever you like. Then you deal with this matrix instead of the singular matrices. Then, for the small perturbed matrix E, then you don't have to think about errors. You can give a whole control of it for the invertible matrix. You can use all the theorems that you have learned. And as you see, the differences are all controllable with the matrix norms. So, when you start it, always you don't start with the original one. You just make some changes. So, construct a matrix that you will not face any difficulties and any critical situations. But still, the difference is very small and controllable by yourself. Then you got the conclusion, then you can always reinterpret it to give the answer that you like to give for the original problems. And so those techniques like matrix norms and those are mathematical knowledge that you can use to proceed your argument. And also in that process, you can use lots of tools, computational tools and theoretical tools, and previous lemmas and theorems and all others related to the matrix. Okay? Okay. Yeah, definition. A is called ill conditions if condition number is large. If A is called well conditions if condition number is small, it's near 1. A is called perfectly conditions if condition number is equal to 1. Okay. So it's invertible, then it's perfectly conditioned. Another thing. If U is a unitary matrix and this is spectral norm, then you know the condition number is preserved, okay, for the unitary transformation. And in general, condition number of AB is less than or equal to the product of condition number of each. Okay. And since these condition numbers are same, we can use unitarily transformation to make this condition number small. So we have a stable numerical linear algebra algorithm. You can just make changes to have a better systems. And these are the same things, just minor perturbations and operations. Okay, and there are some problems in page 3.375. If eigenvalues lambda mu's are different, then the left eigenvector and right eigenvectors are perpendicular. And this was shown in the previous chapter 1. Actually, we did before. Yes. And there's other inclusion regions. Okay, here you saw this. We have in chapter 6.4. Before we have seen what? Gelshigoryn circles, Gelshigoryn regions, and transpose of it for the row sum, the column sums, and what? We have Olga-Tauskis and Hershey's and many others. But here, there are some other type of inclusion regions other than Gelshigoryn regions. In 1937, Ostrowski gave this. For all the set of eigenvalues are in this region. Here, not only the row sums, he's using row sums and column sums together. How it can be happened? How? Mr. Zhang. what you can think of. How Ostrowski can think of this instead of just one. This comes from Helder's inequality. It's very simple ideas. It worked for the row sums. And it also worked for the column sums. You can just move. You can make a shift from one to others. Okay? As you hear, you see the whole Helder's inequality is like this. For the discrete version, this is condition for that. Okay? Here, if alpha is equal to 0, then it's a Cauchy-Gordon region for the column sum. If alpha is 1, it's Cauchy-Gordon theorem for the row sums. Okay? Let alpha is between 0 and 1, then we give some perturbations then to make the inclusion. Then just a simple, very simple calculations. Just Helder's inequality was adopted here, and all others are just simple calculations. As you see here, we can have this. Just to start from the same thing that we start for the Cauchy-Gordon theorem, just to do it. But here you adopt the Helder's inequality. Then just draw it. Then what you have is this. Here. But as you see here, just take what? Take. But as you see here, this cannot be happen. Okay. We have this. But if this is, then we cannot have this. So that means there exists some i's which satisfy this. Here, so this is what we have. Then take 1 minus alpha power here and move these two here. That gives us this. This gives a radius for the i's laws. Okay, just this works for the all i's. So all we have to just take a union of it. Then all eigenvalues are here. That's Ostrowski found that type of generalization. In 1946, Brouwer found another generalization. Every eigenvalues are in the overs of Cassini of this many. So union of this many of overs of Cassini. This is called the overs of Cassini. All eigenvalues is in here. This is a Brouwer's generalization. And proof is also very similar. You just start from AX equal lambda and use the same techniques that we have seen. Just the calculations. We start from this is just a typical start point of the proof on the eigenvalue localization problems like this. So lambda is in here. Lambda is in the region like this. This is called the overs of Cassini, something like this. Okay, so corollary says if it satisfies one of these conditions, then A is invariable. Instead of that, we have this. It's from the Brouwer's overs of Cassini. Okay? If combining those two theorems, then it will have 6.4.11. So the next question is this. Here, before we had the theorem for the one diagonal entry and one deleted row sum. Now we had two. What happened? For three. And what about? Is it true? If we can expand it, then it will be so nice. Isn't it? So everybody tried it. It was failed until 1982, where Richard Broaldi found the right generalization of it. So for M, what if the eigenvalues, whether the eigenvalues is in this region or not, union of this. So this is generalization. When it will be true? So this is so for M there are this many of sets, and when M is equal to 1, this is a Gelshigorn disks of N, and N is equal to 2, we have this many of ovals of Cassini. Then when M is greater than or equal to 3, then how? True or not? Conjecture. This conjecture has been around for about 30 years. Okay? So, in this case, as you see, this doesn't work. So, everybody, many tried it. And Brouwer's generalization was failed over and over again until think about a perturbation theory like this. If these epsilons are 0, then there's nothing we can do. But if we give some minor changes on it, then we can think there was no path here. But if we just give a very small perturbation, then we can have what? We can have a path. We can have a strongly connectedness. We can have a irreducibility. That's like that. So with this, yeah, we can think about the direct graph of that perturbed matrix, and then we can think of, we can use the theorems like that, and that turned out in this way. Strongly connected if and only reducible. Now we define A is weakly reducible. Weakly irreducible. If and only if gamma of A is weakly connected, and this weakly in irreducibility gave if and only if for all epsilon A of I has at least one non-zero off-diagonal entries, such that the sequence this of A non-zero entries for which K1 is equal to J1 and Km is equal to I. With this new definition, Professor Brualdi in 1982 gave this generalization. If A is weakly irreducible, then eigenvalues are all in here. It's not one. We have M of them. Okay? With the new definitions. This cycle. And one interesting is that this Brualdi theorem gave a sharper bound compared to the previous theorems for the irreducible. Okay? Okay, that's the generalization of it. And this is one more. Brualdi's theorem, when A is irreducible, and the boundary point lambda. This is a generalization of Brualdi for the theorem for the eigenvalue, which is on the boundary of one circle. Yeah, we can do the similar things, which was done before, with a new concept. Corollary, weakly reducible and this, or reducible in this. It applies to the bottom. Yeah, sufficient for. So if this satisfied, then we can say the A is invertible matrix. If this is satisfied, then we can call A is invertible. Okay, yeah. Let's conclude that with theorems. Let A is a weakly reducible, and then if this hold, then we can tell the matrix A is non-singular. Matrix is non-singular, and the consequence of it is if A is weakly reducible, then eigenvalues of A, lambda I, is in all eigenvalues are in the union of this. Then we have some consequences like this. If it's irreducible, then here we have inequalities like that. With the strict inequality for at least one cycle, then so all the previous theorems are beautifully generalized to not only one, but two, but all general terms. Okay? And last corollary. principle, then we can also use the Helder's inequality to have this. And all of this can be found on the web. I can show you these Cauchy-Green region theorems. What happened? I made the Java tools for the Cauchy-Green theorems and also the overs of Cassini as well. Okay, so you can find my website for my first page of my home page. Then you will see the G-circle theorems. You go in, then you will check the Java tools that we developed to check the theorems that you have learned today for the location of eigenvalues. Okay. Any questions on chapter 6? I want you to solve at least more than two problems from chapter 6 to conclude your finals. Any questions?